Hello dear students. In the last lecture we have taken a case of spherical shell and we found the electric field inside, outside and at the surface of the shell. Now in this lecture we consider a solid sphere of radius r having a volumetric charge density rho, and we want to find the electric field inside, outside and at the surface of the solid sphere. And we assume that the electric field is everywhere radial and is spherically symmetric. Now, in the first case, we want to find the electric field outside of the sphere. For this, we consider a Gaussian surface of radius r, which is greater than the radius of a sphere. And we take a point P where we choose a surface area ds at point P on which the electric field is normal to the surface area. And the angle between the electric field and the surface area is 0. Now the total flux through the Gaussian surface is equal to closed integral E dot ds, that equal to closed integral E ds cos of 0. Because the electric angle between the electric field and ds is 0, so we have cos of 0 here, which goes to 1, and we get electric field and times closed integral ds. And the surface and the area of the Gaussian surface 4 pi r square. So we replace closed integral ds by 4 pi r square. The charge enclosed by the Gaussian surface is q. And now by applying the Gauss's law, closed integral E dot ds is equal to q over epsilon naught. And by equating the Gauss's law with this derived equation, we get electric field is equal to q over 4 pi epsilon naught r square. Here we can see that the field outside of the sphere is like that of a point charge. And the second result is that this is also same field like in the case of charged shell when we found the electric field outside of the shell. Now, in the second case, we want to find the electric field on the surface of the sphere. So for that, if we decrease the radius of a Gaussian surface up to the Gaussian sphere up to the surface of the sphere, then we get electric field is equal to q over 4 pi epsilon naught capital R square, and capital R is the radius of sphere. Now, how both results look like if we plot them in the form of graph, where the electric field versus the distance from the center of the sphere. You can see here when you are at exactly at the surface of the sphere, you have a maximum electric field, and when you move away from the surface of the sphere, electric field decreases. This is what we have the result for the case of outside of the sphere. Now, in the case of inside of the sphere, let's take a Gaussian surface of radius r now inside of the sphere, and we take a point P where we choose a surface area ds on which the electric field is radial and symmetric all over the Gaussian surface. And now the total charge inside the Gaussian surface, that would be q is equal to rho v, where rho is the charge per unit volume, and this volume is the volume of a Gaussian surface, and that is 4 over 3 pi r cube. Now by applying the Gauss's law, which is closed integral E dot ds is equal to q over epsilon naught, and now by putting the values of ds, area of the Gaussian surface, and q, the total charge inside the Gaussian surface. So we have electric field times 4 pi r square is equal rho into 4 over 3 pi r cube. So we get electric field is equal rho r over 3 epsilon naught. It shows that the electric field inside of the sphere is proportional to the distance from center. So if we see this in a plot, we have a straight line exactly at the center, of the sphere, you have a zero electric field. Once you move away from the center up to the surface, it increases, it increases, and once you reach at the surface, the electric field is maximum, and when you move away from the surface, electric field decreases. Okay, dears, this is all about the today's lecture. If you like the video,